Well, welcome back, fellow students from spring break. So, final trimester or hexmester. And then we have summer vacation. So, we are going to begin our exploration of rational functions. But before I actually get to rational functions, let's review some things you have learned through the school year. Okay, we started way back in September with linear functions of the form y equals mx plus b. So m is the slope and b is the y-intercept. So if I had the equation y equals 2x plus 1, my y-intercept was at 1. The y-intercept is when x is 0. The y-intercept would have been 1. When x is 0, 2 times 0 is 0 plus 1, so my y-intercept would be 1. And then my slope would say go up 2 1 over 1, and that will be my linear equation. So y equals 2x plus 1. So we initially began with linear functions. And then we moved on to quadratic functions like y is equal to x squared. And if you recall, it looks like that. So when x is 0, y is 0. When x is 1, y is 1. When x is 2, y is 4. And so 1, 2, 3, 4. And then we have symmetry. So we had the happy graph. So that was y equals x squared. And then we had polynomials. We worked with polynomials. So for example, like y is equal to x cubed. Remember that kind of looked like this going through it kind of looked like that as an odd function. Or maybe we had something like y is equal to a fourth degree polynomial. I don't know, maybe something like x to the fourth plus 2x squared plus 1 or whatever. And maybe that looks like, so I'm not going to draw that in the coordinate plane, but that may have looked something like this here, right? It may have looked something like that. And then we looked at so we had the linear functions, quadratic functions, and then we had polynomials. We had third degree polynomials and fourth degree polynomials. And then the last thing we looked at right before the break was, let's see here, it was exponential functions, right? Functions that grow very fast. So maybe it went something like that. So that was maybe like y is equal to 2 raised to the x. Or maybe something like this here. It was decay function, and that may have been something like y is equal to 1/2 raised to the x. The multiplier was less than 1. And then we had our log functions, logarithmic functions, and they look something like that. Okay, so we looked at all those functions. Now we're going to begin rational functions. So what do we mean by rational function? Well, a clue is rational meaning ratio, ratio meaning fractions. But before we actually get into looking at working with rational functions, let's cover some terminology here. So our objective today is we're going to look at solving problems involving direct, inverse, or joint variation. Okay. So before we actually get into rational functions, we have to look at variation, and in particular inverse variation. But we'll also take a look at direct and joint. So let's take a look at direct variation is a relationship between two variables, x and y, that can be written in the form y is equal to kx. That's very similar to a linear function, right? Y is equal to a slope times x, where k does not equal 0. In this relation, k is the constant of variation, and we'll see why it's called the constant of variation. For the equation y is equal to k times x, y varies directly as x. In other words, as x increases, y is going to increase. Okay, y depends on x, but as x increases, y will increase. For the equation y is equal to k times x, y varies directly as x. Likewise, I can also say that y divided by x is equal to k. All right, and that's just using algebra. So if y equals k times x, then if I divide both sides by x, I get y over x equals k. All right. Now, I just looked at a linear equation when I began reviewing the equations we looked at. For example, I looked at y is equal to 2x plus 1. Well, that was a linear equation, but direct variation equation is not much different than a linear equation, with the exception we don't have a y-intercept. So when b is equal to 0, we're just left with y is equal to m times x, or y is equal to kx. It's a direct variation equation, or y divided by x equals k. In other words, if we take every value for y and divide it by its value for x, we always get the same k. So let's take a look at an example here. So to determine whether each data set could represent a direct variation equation, again, direct variation, y is equal to k times x, or dividing both sides by x, y divided by x equals k. So if I take each k and divide it by x, and if that's always the same, if it's constant, then we have a direct variation equation. So notice here for number 3 I do. 6 divided by 2 is 3, and that equals 12 divided by 4, that's 3, equals 18 divided by 6, that's 3, and 24 divided by 8. It all equals 3. Okay, so that is a direct variation equation. In my equation, so that would equal k. So k would equal 3. Okay. K equals 3. Y divided by x. If it's always the constant, that's a direct variation equation. So the equation for this one then would be y equals my k, which is 3x. Y is equal to 3x. Don't believe me? 3 times 2 is 6, 3 times 4 is 12, 3 times 6 is 18, and 3 times 8 is 24. It's a direct variation equation. All right. Now, if I graph that here, you'll see that's this one here, y equals 3x. So again, there's no y-intercept for direct variation equation. My intercept b is 0, so that means the equation, the line goes right through the origin. So y is equal to 3x. Y equals 3x there. All right, so every direct variation equation is going to go through the origin. Okay, because the y-intercept b is 0, direct variation equation. Or every time we take y and divide it by x, we'll get the same value. In this case here, it was 3. All right, direct variation equation. Now, number 4 is not a direct variation equation, because if I take each y and divide it by x, 9 divided by 2 would be 4.5, and then 15 divided by 4 would be 3.75, and then 21 divided by 6 would be 3.5, and then 27 divided by 8 would be 3.325. So that is not a direct variation equation. In other words, k is not constant. Okay, for direct variation equation, if I take each y and divide it by x, okay, I'll get the same value. 4 was not a direct variation equation. It is, however, a linear equation. Okay, the equation that would explain the data in that table would be y is equal to, let me see, I believe that would be 3x plus 3. So let's see here. Let me write that in blue. So that would be y equals 3x plus 3. When x is equal to 2, 3 times 2 is 6, and 6 plus 3 is 9. 4 times 3 is 12, plus 3 is 15. 6 times 3 is 18, plus 3 is 21, and 8 times 3 is 24, plus 3 is 24. So that would be a linear equation, and that's represented here. My y-intercept is 3. And my slope says go up 3, 1, 2, 3, and over 1. Okay, but it is not a direct variation equation. It does not go through the origin. In other words, The y-intercept is not 0. Okay, so 3 was direct variation because each y divided by x was the same, but number 4 was not. Each direct variation equation will always go through the origin. Right. Now, we don't do a whole lot with direct variation equations in this chapter. It's just an introduction into variation equations, which I'll continue to explore. So that's direct variation. Now let's take a look at inverse variation. Inverse variation describes a situation in which one quantity increases. So for example, as x increases, another quantity, call it y, will decrease. Okay, so y will decrease. They go in opposite directions. Direct variation, you went in the same direction. As x increased, y increased. What did I say? Direct variation, as x increases, y increases. Inverse variation, as x increases, y decreases. So inverse variation describes a situation in which one quantity increases and the other decreases. For example, the table shows that the time needed to drive 600 miles decreases as speed increases. So as speed increases, or as x increases, then the time to drive 600 miles, y, would decrease. Inverse variation. This type of variation is an inverse variation. An inverse variation is a relationship between two variables, x and y, that can be written in the form y equals k divided by x. So as you see here, no matter what the value is for k, as x increase, well then y will decrease. As my denominator gets bigger, then as x increases, then y will decrease. As my denominator gets bigger, then the value for y will decrease. Inverse variation. For the equation y is equal to k over x, we say y varies inversely as x. Now also note here, y equals k over x. If I multiply both sides by x, I'll get y times x equals k. Okay. In other words, if we always take y and we multiply it by its corresponding x, if that's constant, then that is inverse variation. And we'll take a look at that. So here we have this equation here. As speed increase, the time to drive 600 miles decrease. And I want you to notice, though, that as I take each x and multiply it by y, I always get the same value. So 30 times 20 equals 600. 40 times 15 equals 600. And then 50 times 12 equals 600. So in this problem here, my constant is 600. So my equation would be y equals 600 divided by x. Again, k is equal to y times x. I took y times x, I got 600. I took y times x, I got 600. I took y times x, and I got 600. K is 600. So my equation that explains that then would be y equals 600 divided by x. Okay, so if I took 600 and divided it by 30, I'd get 20. That would be my y. And if I took 600 and divided it by 40, that would be 15. That would be my y. Now, for inverse variation equations, we get this one half of the graph. This is only one half of the graph. We'll look at the other half a little later. But I want you to notice here that as x increases, y decreases. Okay. Again, what did we have when x was equal to 30? We had 20. So when x was equal to 30, we had 20. When x was equal to 40, we had 15. When x was equal to 50, we had 12. If x is equal to 10, 600, so y will equal 600 divided by 10, and that would be 60. So let's see here. Yeah, there we go. X is equal to 10, y is equal to 60. So, there. All right, so again, the important point here, that if you take each x and you multiply it by y, y times x, x times y, if that remains constant, then we have inverse variation. So let's look here. Given y varies inversely as x, so right now I know that my equation is going to be y equals some k over x. Y varies inversely as x. And y equals 4 when x is equal to 10, write the inverse variation function. Find y for given values of x is equal to 20, 40, and 60. So again, the first step with this here, we want to find k. We have the equation is inverse variation. We have y equals k over x. Okay, step 1. We have to solve for k. We have to find k. So what do? Well, we multiply the left side by 10. Or remember, again, k, going back up here, k is equal to y times x. Yeah, come on, give me my k is equal to y times x. So in order to find k then, I have to multiply both sides by 10. So multiply both sides by 10. So k is equal to 40. And so k is equal to 40, so my inverse variation equation is y is equal to 40 over x. Y equals 40 over x. And then the second part, for y, find y for given values of x is equal to 20. Well, y would equal 40 over 20. That would equal 2. 40, so y would equal 40 over 40. That would equal 1. Or 60, y would equal 40 over 60. Well, that would just be 2/3. I want you to notice each time x increases, y is decreasing. Okay. Inverse variation. And let's look at the next one. Given y varies inversely as x, so again y is equal to k over x, or y times x equals k. Write an inverse variation equation and find y for the given value of x. So when y is equal to 2 and x is equal to 7, so y is 2, so 2 times and x is 7, so that's going to be my k equals k, so 14 equals k. And so now my inverse variation equation is going to be y equals 14, that's k, over x. Find y for the given value of x. So when x is equal to 2 then, so when x is equal to 2, y will equal 14 over 2 equals 7. Okay. And try the next two on your own. Let's look at a word problem here. The time t needed to complete a certain race varies inversely as the average speed. So t varies inversely. So t equals k over speed, if you will. T varies inversely as the average speed. If a runner with an average speed of 8.82 miles per hour completes the race in 2.97 hours, what is the average speed of a runner who completes the race in 3.5? and 3.5 hours. So again, we start with the inverse variation equation. T is equal to k over x. Then we take the information given to us. They say the time, so T, if a runner with an average speed of 8.82 miles per hour, so that's speed, so that's S. And let me do this, so that's S. Completes the race in 2.9 hours, so that's T. 2.97 hours. Okay, so we have to find K. So again, we have to multiply T. So T times S equals K. So K equals 26.1954. And so now we have our inverse variation equation. And then the second part of this, what is the average speed? So we're looking for S for a runner who completes the race in 3.5 hours. So we have 3.5 equals, we know K is 2.61954. We don't know S. That's what we're looking for. What is the average speed? So if I multiply both sides by S, I'll get 3.5S equals 26.1954, and then I can divide both sides by 3.5. And I'll get S is approximately equal to 7.48. Okay, so the speed would have been about 7.48 miles per hour. Let's look at the next one. The time T it takes for a group of volunteers to construct a house varies. So T varies inversely, K over as a number of volunteers. So T varies inversely. So T is equal to K over V. If 20 volunteers, so V is 20. If 20 volunteers can build a house in 62.5 working hours, so time is 62.5, how many working hours would it take 15 volunteers to build a house? So again, first of all, we have to find K. So in this case, T times V equals K. So we have 62.5 times 20 equals 1250. So now we know our inverse variation equation. We found our K. T equals 1250 divided by V. And then the second part says, how many working hours? So we're looking for T in this case here. The time T, how many working hours would it take 15 volunteers? So the number of volunteers is 15 to build a house. So 1250 divided by 15 is 83 1/3 hour. Okay, so with all of these, what you want to do first, you want to find K. Once you found K, you write your equation, and then you use your equation and the information they give you to find the missing variable. That's inverse variation. Let's look at joint variation. The joint variation is a relationship among three variables that can be written in the form y is equal to k times xz, where k is the constant of variation. For the equation y is equal to k times xz, y varies jointly as x and y. Let's just look at one example. The volume V of a varies, so V varies jointly, so we have some K, as the area of the base B and the height H. Okay, so this is joint variation. It's like direct variation almost, but it's joint. We have two variables. So when the volume is 12 pi feet cubed and the base is 9 pi feet cubed, and the height is 4, well, we can find k. So we just substitute any information we have. So 12 pi, that was the volume. So the volume, 12 pi, and then k is k, and then the base was 9 pi, and then the height, they gave us here was 4. Okay, so when we solve that for k, we'll get 1/3 is equal to k. So there's my equation there. Volume is equal to 1/3 times BH. And then find the base then when the volume is 24 pi feet cubed and the height is 9. So again, we use our equation that we found, and then we just substitute the information we have. So we have 24 pi equals 1/3 b times 9. So that would be 24 pi equals 3b. And then dividing both sides by 3, you'd get 8 pi. Would be the base, 8 pi feet squared. Let's look at another one. The volume V of a rectangular prism varies jointly as the length L, so V equals K times L, and the width W varies jointly. So V is equal to K times L times W. The volume is 224 cubic feet when L is 8 and W is 4. So let's find K. So we have the volume is 224 cubic feet, and when L is 8 and W is 4, so you get 224 equals 32K. So 224 equals 32K. Dividing both sides by 32, you get K is equal to 7. Okay, so now we have our joint variation equation. Volume is equal to 7 times L times W. Find L when V is 210 cubic feet and the width is 5. Okay, so we set volume is equal to 210 cubic feet and the width is 5, and so we'll get 210 equals 35L, and dividing both sides by 35 we get 6 is equal to L. So again, with all of these, we just use the equation given. We solve for K, we write the equation, and then we use the equation to answer the questions related to the problem. So that is joint variation. So we've looked at joint variation, we've looked at inverse variation, and then we've looked at direct variation. Now, we have one last thing called combined variation. Combined variation is a relationship that contains both direct or combined variation and inverse variation, okay? We combine a lot of things here. So, all right, we combine a lot of things. So we can have something y is equal to, I'll just use k times, I'll just use some other variables. K is always some constant. So like m times n over anything z. Okay, so again here this would be joint, both direct or joint variation, I should say. That's not. Combined variation is a relationship that contains both direct or joint variation. We just looked at joint variation there where we had two variables. So combined variation is a relationship that contains both direct or joint variation and inverse variation. So notice here, okay, m times n is joint, but then I'm dividing by z, which is inverse, okay? Or we could have, so that will include both inverse variation and joint variation, or we could have y is just equal to k times x, if you will, divided by z. So that would contain direct variation, y is equal to k times x, and inverse variation because we're dividing by z. Okay, so this would have been joint and inverse, and then this would have been direct variation and inverse. All right, now a good illustration of combined variation using joint variation and inverse variation is Newton's law of gravitational force, which basically says like the force between two heavenly bodies like the earth and the sun, if you will. Let's say this is the sun. The gravitational force between them. So we would say, I like to write it like this here, the gravitational force is proportional to some constant of variation times the product of the masses divided by the distance squared. Okay, and that will make sense. Imagine if you have two magnets and they're kind of small, but now you increase the size of those magnets. Well, the force between those two magnets should increase. It should vary directly. So, times the product of the masses. But then as you separate those two magnets or you spread them further and further apart, the distance gets farther and farther apart. And so the gravitational force, if you will, the force between them should decrease. And so that's why we divide by r squared, or the distance between them. All right, and I've always considered this here the most important equation in the universe because that's the glue that holds the universe together. Without it, we'd be an asteroid. Okay, we would not exist. Okay, but the gravitational force is proportional to the product of the masses, the earth and the sun, divided by the distance between them. And it could be anything. It could be earth and the moon, or any two heavenly bodies. All right, a very good illustration of combined variation. Probably the most important combined variation you'll ever see because it explains our existence. So let's just take a look at just one problem here. The volume V of a gas varies inversely as the pressure, so V varies inversely as the pressure, so V equals some constant as a pressure P over, and directly as a temperature T. So again, here we have direct variation. So direct variation, y is equal to k times t, but then we have inverse variation, volume, or v is equal to k times t, and then we have inverse variation, v is equal to k over p. So we combine them together. So the volume V of a gas varies inversely as a pressure P and directly as a temperature T. A certain gas has a volume of 10 liters. So V is equal to 10. We're just substituting here. V is equal to 10. A temperature of 300 kelvins, so the temperature is 300. And a pressure of 1.5 atmospheres. Here, let me do this. So this is the temperature, and then the pressure of 1.5. Solving for K, if I multiply 1.5 by both sides, I get 150 equals 300 K, or 15 equals 300 K, and then dividing by 300, I would get 0.05 equals K. So my equation then, I found K, as we always do, we want to find K, and so now I can write my equation. The volume is equal to 0.05 T over P. And then we can use that to answer the next problems. If the gas is heated to 400 K and has a pressure of 1, what is this volume? Okay, so here we're just solving for volume. So we just substitute. We use the equation and we substitute 400. We substitute 400 for the temperature. And we substitute 1 for the pressure. We substitute 1 for the pressure. And then we get 20. So 20 liters. Okay, so that's it. So we've covered direct variation, inverse variation, joint variation, and then combined variation, which combines everything, either joint and inverse or direct and inverse. But the process is the same. You start with the equation. Direct y is, oops, here. What equation are we talking about? What direct? Oh, come on. What direct variation, inverse variation, joint variation. Y is equal to k times m times n or whatever. Or maybe I'll use some other variables. S times t, it doesn't matter. And then we have combined variation where we could have y is equal. We have both direct variation, y is equal to k times x over some variable. So that would be combined using direct and inverse. Or we would have y is equal to k times like ab. So that would be joint variation divided by some variable z. And that would be inverse. So these are the equations we're working with here. Okay, but in each case here, case you first have to find k. You have to find k. Doesn't matter. The process is the same. And then once you find k, then you can write your equation using k and then solve it to answer the rest of the problems.